Through the depths of the earth, where darkness, pressure, and metal collide, rise the silent wonders of humankind. What was once a science fiction dream has now become proof of human ingenuity. The power to connect two worlds through colossal tunnels. Every meter drilled is not just a triumph of precision engineering, but a mark of determination, the force that drives us to venture where no one has ever gone before. Deep within the mountain's shadows, the machines keep turning, each rotation echoing the heartbeat of civilization. This is more than tunnel construction. It is the art of carving pathways to the future, an extraordinary journey that Mandarin Tech will take you through in today's video. Hidden behind the majesty of the mountains lies a harsh reality that humanity has faced for centuries. In 1991, a catastrophic landslide at the Racha Pass claimed more than 200 lives. In 2014, a fierce snowstorm in the Annapurna Range left 400 trekkers missing. And in China alone, over 1,000 deadly landslides are recorded every year. These grim numbers serve as nature's reminder of human limitations, but also as the driving force behind China's relentless search for a safer, more sustainable path. Their answer was to go through the mountains. Massive tunnels were built, allowing vehicles to travel straight through instead of winding along dangerous mountain passes, cutting travel distance, saving fuel, and reducing emissions. More importantly, they turned peril into safety, transforming rugged peaks into vital arteries of the future, a testament to humanity's ambition to conquer the mountains and redraw the map of global transportation. To turn the dream of tunneling through mountains into reality, every project begins with a plan detailed down to the smallest element. After determining the route to be connected, engineers begin the first stage, a comprehensive geological survey. They drill exploratory holes dozens of meters deep, sometimes more than 300 meters into the mountain, to collect rock samples and measure hardness, porosity, and groundwater pressure. Each sample helps them better understand the mountain's internal structure, pinpoint fault zones, weak rock layers, and areas prone to landslides. At the same time, environmental specialists assess how the project might affect the surrounding landscape, from erosion risks and changes in underground water flow to impacts on nearby ecosystems. All this data is digitized and fed into 3D geotechnical simulation software, allowing engineers to see through the mountain and calculate the optimal slope, alignment, and curvature radius. From these measurements and simulations, the safest and most efficient construction plan is finally chosen. Amid dense rock and heavy darkness, the project is given its first breath, the ventilation system. At depths of hundreds of meters, where pressure, dust, and heat can make the air toxic within minutes, engineers must create an artificial network to sustain life underground. From the construction center, vertical shafts are drilled up to the surface, each about 4 to 6 meters wide and up to 200 meters high, bringing in fresh air while expelling exhaust gases. Inside, sensors constantly monitor oxygen levels, temperature, and toxic gases, coordinating powerful jet fans to keep airflow steady. These ventilation shafts are built using the raise boring technique, where the drill head is operated from inside the tunnel and pushed upward toward the surface with near-perfect precision. Once completed, the entire network becomes the lungs of the project, allowing hundreds of workers to labor for hours beneath the mountain while still breathing the air of life. Outside, the construction site is shrouded in a haze of dust, while deep inside the mountain, a colossal machine is slowly being assembled, the tunnel boring machine, a true symbol of the modern infrastructure era. Positioning this giant for its first operation is a highly complex process that demands absolute precision and seamless coordination among hundreds of engineers. The entire system is delivered to the site through hundreds of specialized transport vehicles, each carrying modules weighing from dozens to hundreds of tons. From the supporting frame and control cabin to the hydraulic systems and the cutter head, the heaviest component, weighing over 1,500 tons and nearly 15 meters in diameter. Auxiliary tunnels are widened and temporarily reinforced with steel and sprayed concrete to make room for these massive components. In the confined space illuminated by hundreds of industrial lamps, the modules are connected and aligned using laser sensors with a tolerance margin of no more than 5 millimeters. Powerful hydraulic jacks lift the cutter head into position, linking it step by step with the body and tail sections according to a predetermined sequence. Once fully assembled, the entire tunnel boring machine stretches nearly 100 meters long, the equivalent of a 30-story building laid on its side, with thousands of mechanical parts perfectly fitted together, forming a unified steel giant ready to pierce through the solid heart of the mountain. From the central control cabin, the electrical, hydraulic, and pneumatic systems come alive. In an instant, the mountain trembles slightly. The tunnel boring machine begins to move. Nearly 100 meters long and weighing over 3,000 tons, the machine advances slowly yet powerfully, with thousands of mechanical components working in perfect harmony. At this stage, the cutter head is already buried deep in the rock, while the rear section is still being assembled in the launch chamber, a process requiring precise coordination between power, water, air, and conveyor systems that must run without interruption. At the front, 4 massive hydraulic cylinders press the cutter head against the rock with up to 500 tons of force. 23 alloy discs spin with immense torque, crushing layers of rock as hard as steel. Each drilling cycle advances about 1.2 meters, taking roughly 30 minutes and repeating more than 50 times per shift. The crushed rock is collected and carried out by an automated conveyor, while high-pressure water jets constantly cool and clean the cutter head, reducing friction. Once a cycle ends, the gripper shield pushes forward, hydraulic clamps lock onto the tunnel walls, and the next cycle begins. This rhythm, press, release, advance, drill, repeats endlessly, day and night, until the tunnel is complete. In monumental projects like Europe's Santa Lucia Tunnel, with a TBM diameter of nearly 16 meters, or Switzerland's 57-kilometer Gotthard Base Tunnel, the machines operate 24 hours a day with unmatched precision. Yet today, China leads this underground frontier, with over 1,000 TBMs simultaneously carving railways, subways, and hydroelectric tunnels, a true symbol of its determination to conquer the depths with technology. Which nation's tunneling innovation impresses you the most? Although the tunnel boring machine has ushered in a new era of modern construction technology, not every type of geology is suitable for this colossal machine to operate at full efficiency. In areas with soft, porous, or unstable rock layers, where even the slightest vibration could trigger a collapse, engineers must return to a seemingly old yet time-tested method: controlled drilling and blasting. This technique requires a sophisticated blend of rock mechanics, explosive chemistry, and the highest level of safety control. The process begins with a detailed geological survey, seismic measurements, and determination of the safe vibration limits. The construction team then drills hundreds of holes, each 5 to 6 meters deep, arranged in a fan pattern to direct the explosive energy evenly through the rock. Before every detonation, all wires and electric detonators are checked for resistance to prevent leakage or short circuits. Geological data is fed into 3D simulation software to precisely calculate the amount of explosive and the delay timing between each blast point, ensuring the explosion propagates in a controlled direction. Each hole is loaded with 80-100 kilograms of explosives, combined with fast and slow-reacting chemical agents, so that the blast unfolds in a preset sequence. When the warning signal sounds 3 times, the ground shakes and the rock shatters exactly as designed. Immediately after the explosion, 2 high-power ventilation ducts are activated to extract toxic gases and dust. About 20 minutes later, the engineering team enters to measure tunnel wall deformation, clear loose debris, and spray a temporary layer of shotcrete to stabilize the rock ceiling. Despite its advantages in speed and cost, the drilling and blasting method demands absolute precision. Even a slight miscalculation could cause cracks, water leaks, or collapses. That's why modern tunneling projects now integrate vibration sensors, digital simulations, and real-time monitoring, allowing this traditional technique to work alongside TBMs, maintaining its irreplaceable role in contemporary tunnel construction. As drilling and blasting techniques began reaching their limits in weak and complex geological zones, the tunneling industry entered a new era, one that is more sophisticated, safer, and more adaptable. This is the sequential excavation method, also known as the New Austrian Tunneling Method, NATM. Developed in Europe during the 1960s, it marked a turning point in tunneling history, as engineers learned not just to resist nature, but to work with it, using the natural strength of the surrounding rock to carve pathways through mountains. What makes this method unique is its construction philosophy. Instead of relying entirely on artificial support structures, it harnesses the natural load-bearing capacity of the ground itself, turning the surrounding rock mass into part of the tunnel's structural system. Each section of the tunnel is excavated only about 1 to 1.5 meters at a time and immediately covered with a 25-centimeter layer of sprayed concrete to stabilize the roof and walls. Rock bolts and steel mesh are then installed to distribute stress, creating a natural load-bearing arch between the rock and the concrete. Once monitoring data confirm that the surrounding stress has reached equilibrium, the permanent lining is built using cast or high-pressure sprayed concrete, forming a durable structure for the entire tunnel. This method can reduce reinforcement materials by 30–40%, while minimizing vibration and surface settlement, a crucial advantage for tunnels near residential areas or existing infrastructure. However, achieving such precision requires continuous geotechnical monitoring, with hundreds of sensors attached directly to the tunnel walls to measure deformation, stress, and displacement in real time. All data are transmitted to a central control room, where engineers constantly analyze conditions and adjust construction methods accordingly. By listening to the earth and adapting to even the smallest changes, this approach has become one of the most significant advances in modern tunneling technology. Deep inside the mountain, the drilling has stopped, but the work is far from over. Engineers, now carrying measuring instruments instead of drills, quietly enter the tunnel, where every meter of concrete must prove its strength. Pressure sensors and ground-penetrating radar scan the walls, detecting cracks thinner than a hair. High-frequency ultrasound and 8K optical cameras inspect every bolt and seal to ensure flawless safety. In the control room, hundreds of real-time indicators track the tunnel's lungs, jet fans, smoke sensors, drainage pumps, and a 10-megawatt backup power system, all tested under strict NFPA 502 and EN 505I45 standards. Every reading and vibration is recorded and analyzed until perfection is reached. Only then is the tunnel declared ready, a true symbol of precision and human resilience beneath the earth. As the first vehicles begin to pass through, the tunnel enters its full operational phase, where every system must perform with absolute precision. Along its many kilometers, more than 1,500 sensors are embedded in the tunnel walls, continuously recording data on vibration, pressure, humidity, and water leakage with constant updates. This information is transmitted to the control center, where intelligent monitoring software analyzes the data and issues early warnings if it detects even a 0.2 millimeter deformation in the concrete structure. Each year, maintenance is carried out on a strict schedule. The 200 kW jet fans, lighting systems, smoke detectors, signal boards, and cameras are all inspected, cleaned, and recalibrated to maintain peak performance. Drainage channels over 1.5 meters deep are regularly cleared, while 1,000 liter per minute pumps are tested to handle heavy rain scenarios. Maintenance work usually takes place at night, when traffic flow drops below 20%, minimizing disruption for drivers. When the first light shines into the tunnel, it marks more than the completion of a project. It is the result of years of research, excavation, and assembly measured to the millimeter. Every mountain tunnel stands as proof of human engineering and endurance in the quest to conquer nature. It is not just infrastructure, but a masterpiece born from the collaboration between engineers, machines, and data, where every decision is guided by absolute precision. And if you want to discover how technology and humanity are transforming the world together, don't forget to like and subscribe to Mandarin Tech, where technology isn't just presented, but told as a story of our ongoing evolution toward the future.